Thank you very much, Ernie. Let me just start by saying that if anyone would like to look at my overheads in more detail, I put copies up at the back of the room on that poster board. They'll stay there until somebody else leaves the space. As you realize, this is very much another introductory lecture in that I'm not talking primarily about friction. But all the same, whatever type of friction we're concerned with, a satisfactory model of friction obviously must account for data of two sorts. Firstly, the magnitude of the frictional force that's transmitted across the interface, and secondly, the rate at which mechanical work is dissipated through friction. And both these quantities, they may or may not depend upon the presence and the magnitude of some kind of adhesive force, such as intermolecular attraction across the interface. And here we have a difficulty. When we talk about adhesion, often the terminology is used rather loosely. Adhesion means different things to different people. And you can see that if you look at what I've got on the screen there, the actual units that are being used there for these different quantities are different. If we talk about the well-known adsorption energy of individual atoms, for instance, in connection with a solid such as charcoal attracting gas molecules onto itself, people use units such as electron volts per atom. If we're interested in the forces that two surfaces feel to each other due to intermolecular attraction, in newtons obviously, this is hard to measure because of topics, quantities such as were mentioned this morning, elastic forces, but clearly it is important in everyday life, the way in which emulsion paint works, for instance, latex particles sticking together, or the hard brown stain that you see left behind the basin underneath a dripping water tank. Then, as distinct from attraction, we have a force that is again sometimes called adhesion, perhaps more precisely described by the term adherence or pull-off force. This is the externally applied force needed to separate two surfaces that are touched together. We're seldom aware of this in everyday life, and that's a very important point in connection with friction. We're seldom aware of the fact that when you take two clean surfaces and touch them together, that any pull-off force is required to separate it. And I'll say more about that later. There is the material parameter, in principle, by analogy with surface energy, which I've listed there under the heading D, a free energy of adhesion, or Dupre energy as it's sometimes called. Then there is the whole question of glue. That's what adhesion means to the layman, after all. Coatings stuck to a surface, or glue joints, and all sorts of units have been used to measure that quantity such as I've listed there. So let me just, in passing, say something about this problem of quantifying the performance of coatings and glue joints. If I could just have a slide on, please, to illustrate that. If we're talking about glue joints, coatings, and so on, often these have been specified in terms of the normal force or the transverse force sometimes required to peel something off the surface. So people have even tried to specify them in terms of tensile or shear strengths. Now again, there's a danger of confusion here. That's the last one. I'd like the first one, please. Let me take something like a lap joint for many of the people who use adhesives in engineering structures. The thing about a lap joint is that the braking force required to cause that joint to fail is not proportional. There we are. We have a peeling test on the left and we have a scratch test on the right. A lap joint, the braking force is not proportional to the area of the overlap, And it even depends on the backing. It even depends how stiff the whole structure is. So how can we talk about the strength of a glued joint in such a case? Because to me, at any rate, the word strength implies that there's a maximum stress in newtons per square meter, which that joint will can be subjected to. And that is, in fact, nonsense. But unbelievably, people still do talk about the sheer strength of glued joints. More logical is to talk in terms, to describe the phenomenon in terms of fracture mechanics, involving quantities such as work of adhesion or critical stress intensity factor. So, projector off, please. Let me go back then to the last example, or the last but one example there, which I've got as E, the question of the adhesion contribution to friction. Possibly the most important type of adhesion, as far as we're concerned here, the adhesion component of friction. The strong support for the adhesion theory of metallic sliding friction, as most of us well know. In fact, you can talk about a progression in terms of types of surfaces. If you talk about ultra-thin metal surfaces, normally the junction between them, or very often, is stronger than the bulk of either of the two surfaces. In fact, if you try to pull it apart, it doesn't separate the interface at all. If you then move down progression, which I'm asking you to imagine that the surfaces are progressively covered with some kind of film, then you reach a point where the surfaces can still seize up. But in order to achieve seizure, sliding is needed. Then if the surfaces are progressively still more filmed, perhaps with a thicker oxide layer, you have no gross seizure, but you have high friction and some plucking of material. And if the more and more contamination you have, the lower the friction coefficient gets, and eventually you can reach the boundary lubrication situation. So the adhesion theory of metallic friction. Possible objection that we don't detect any pull-off force in practice, normally, to separate the surfaces. This objection is not necessarily valid. And I'll talk about that later, but just to anticipate a bit, the reason basically is that in order to achieve intimate contact between most types of surface in practice, a normal load is needed. All the same, this does apply to terms such as the strength of the adhesion for the strength of the adhesion is misleading if units of shear stress are used. Now, this question of the connection between adhesion and friction. The whole point about the different ways in which bonds break. This was discussed to some extent this morning. The point is that even in the simplest case, when we have true sliding at the interface, the resistance to sliding that intermolecular forces provide is a different phenomenon, a largely unexplored phenomenon, to the bond breaking that we do when we measure adhesion. And as we'll see later this week, instead of true sliding, we can have shearing or tearing, if you like, of the metallic microjunctions that result in the first place from the gripping action of intermolecular forces. In which case, any values of shear strength that we derive from analyzing friction experiments will very probably bear no direct relation to adhesion parameters. And as we'll see, this is because the energy dissipation mechanism involved is to a large extent involving bulk effects. So we conclude that although there is this strong evidence for the existence of the adhesion component of friction, it is a controversial subject. I like Professor Johnson's term tangential interaction as a less confusing term than adhesion, even if it's not such a compact term to use. We need to think a bit about different types of surface force. The surface forces involved in adhesion are really basically the same as those responsible for the cohesion of solids. We can have electrostatic forces, we can have intrinsically shortly range interactions such as covalent bonding, purely quantum mechanical in nature. And we can have long-range forces such as van der Waals forces, including all the various different types of particular long-range forces that come under the general heading of van der Waals. It's worth making one general point here, and that is that if you compare macroscopic objects, such as particles or large flat surfaces that you can handle, with the behavior of condensed phases and of gases, they are different with regard to the behavior of these long-range forces in practice. If you take gases and condensed surfaces, the forces all turn out to be short range by the time you've worked out what happens, the relative contribution of nearest neighbors, second nearest neighbors, and so on. If you think of van der Waals forces varying as the -7th power of the separation between two molecules, you can see that this must be the case, with the possible exception of ionic solids. If, on the other hand, you take macroscopic particles, when we sum the relevant pair potentials, we often find that the force between two objects is much longer range than in the example that I just considered. It can be of appreciable and measurable value even at distances of more than 100 or 200 nanometers. For example, if you do this integration and work out the van der Waals force between two spheres or a sphere and a flat, you find that it only varies as separation to the -2 instead of the -7. So that quantitative point is worth making. Let me next move to a basic contact mechanics problem that involves adhesion. The same situation that Professor Johnson was talking about this morning, contact between a sphere and a flat. The parameters are involved, with one exception, are the same as what we heard about this morning. You have the geometry, the effective radius, r star, I'm using the same notation as we used this morning. You have the elastic properties. The quantity K that I've got in that formula actually is the same as 4/3 of Professor Johnson's E star.
Excuse me, Hubert, I wonder if you could move over and back. People back there, it's quite hard to read that.
You'd like it as big as possible, that's a good idea.
Yeah, I think if you made it 20% larger.
Yes.
Thanks very much. Yeah, that's
Can you hear me at the back as well? Good. If, as I say, I'd be only too happy to go through any particular details of these at any time, maybe with the help of that poster at the back there. We have the elasticity. Then we have the surface forces, which, as Dr. Moji said in one of the questions today, are characterized by the pre-adhesion energy, which corresponds to surface energy. It's the sum of the surface energies of the two materials involved minus the interfacial energy. Or you can talk about, if you don't like using energy, if you prefer using force, then you can use the particular force law that you decide is involved in the particular situation. And then you have the applied load, which needn't be positive, of course. If there is significant adhesion, the load will be negative. And the problem really is how to relate these quantities. That's what the contact mechanics with adhesion is all about. It was Muller, Yushchenko, and Deryagin about 11 years ago who worked out the rigorous solution to this problem, taking account of continuum elasticity, mechanics, and a Leonard-Jones form of intermolecular attraction. There is no analytical solution to that problem, which is very inconvenient, and there are two approximations which are useful in practice, particularly the second one. There's the DMT approximation, which stands for Deryagin, Muller, and Tabor.What. I've called it the deformed profile approximation here, because the approximation that's involved is that although the DMT model takes account of elastic deformation that's produced by the external node, it neglects any additional elastic deformation that may result as the action of surface forces. And then there is the JKRS fracture mechanics approximation, which involves a balance of energies. You work out the sum of all the relevant energies and you minimize it with respect to whatever variable you want to work with. And the approximation there is that it takes account of all the elastic deformation, including that that's provided by as a result of the surface forces, but it neglects any intermolecular attraction that acts outside the contact region. I've mentioned here, for those who read it, that there is a neck of material that's called out. You actually may have noticed it in the previous overhead. In fact, you can see it in this one. There it is. There's a neck of material there, and the question of the validity of these two models depends on the relative magnitudes of the height of that neck as compared with the intermolecular separation. Let me show you an example of the simplest possible DMT type calculation. There it is. Very simple in that we're neglecting elastic deformation altogether. We have a sphere in contact with the plane. Let's see if we can work out the force of attraction between the surfaces. Did you know that if you put two surfaces together, even if you have no contact area at all, because that's what we have here, if they're rigid, it's a point of contact. There is no contact area. Did you know that even in that case, the adhesion is finite? And that, of course, is because the separation between the surfaces is not zero over a finite area. It's very small over quite a sizable area around that point of contact. Let's calculate the force of attraction. I've drawn an element of force F prime up there, and what we've got to do is add up all those elements, which means that you take the force function and integrate it with respect to area. And that then you can do a substitution, because instead of using the element of area, you can use a geometrical approximation. There it is. You put that in, you do the integration, and you find that the particular force function that's involved actually disappears from the calculation, and that is because the integral of f of z with respect to z, the separation, the integral of f of z with respect to z is by definition equal to the adhesion energy. So we get rid of it that way. And the result is very simple. It's 2 pi times the radius times the adhesion energy W. And that formula was first derived by Bradley nearly 50 years ago. In the case of finite elasticity, then the DMT type calculation, as you'd expect, is more complicated. It's valid if the height of that neck is small compared to the equilibrium separation between molecules across the interface. And it turns out that the conditions for that validity to apply, you get DMT case, if you like, if the adhesion energy is small, and if the radius of the particle or the sphere is small, and if the elastic modulus is large. So small rigid objects of low adhesion energy, DMT approximation is likely to be valid. It's useful in cases of complex geometry. Please interrupt me if there's anything that you disagree with or want me to explain in more detail now. I'm very happy to be interrupted. Let's look in more detail at the JKRS fracture mechanics approximation. The idea there, basically, is that when two surfaces separate, around the perimeter, you have, in effect, a crack. And as they separate, the crack propagates inwards towards the center. So this takes account, as I say, of all the elastic deformation that's involved. The force of attraction is not proportional to the contact area. But for anyone who has not mapped ideas of fraction mechanics, this perhaps is surprising. That if I have a sphere against a flat, if I double the contact area, I might expect that I have twice as much force. That's not the case. What I'll try to show you is that the force varies as the 3/4 power of the contact area. So there it is. We need to define an effective force of attraction. Well, just as an external load is minus the differential of potential energy with respect to distance, we can define an effective force of attraction in terms of minus the differential of the relevant surface energy with respect to distance. There it is. This can replace the tensile stresses associated with intermolecular attraction at the edge for some purposes. So let's see if I can work out how it varies with area. I won't go slow enough for you to follow every step because it is all up there on the poster at the back, but this just gives you a taste of what's involved. This is true not only for contact between a sphere and a flat, but it's true for any axisymmetric geometry. It's a two-stage calculation. The first thing you do is you try to find out how what I call delta, which is the distance moved by the external load, downwards in this case. You want to find out how that varies with load, and what you do is you do a two-stage process. You start by imagining the zero load, and there are no surface forces, zero load and zero adhesion energy. And then you take it to the case where you end up with the correct area that you're going to end up with. And I've used the symbol A here, as Professor Johnson did this morning, for the radius of the contact region. You end up with the correct value of A. And still, you ought to imagine there's no adhesion energy. Therefore, you need to sit on it in order to get that area. It's a rubber ball, you need to sit on it. And the load that you need to do that is called P1. And then you end up in the final state that you want to, in which you have surface forces, you've got the correct value of W, and you have the correct load and the correct area. And you work out the distances here. You have an unknown function of delta 1, because that depends on the geometry, but that doesn't matter. And then you consider the easiest way, with the least amount of algebra, is to consider that quantity with what we're trying to calculate, pi at the bottom of the fraction, 2 pi WA over pi. And from the definition of pi, you find it works out to be just d delta by dA equals dP. And then you use that formula that we've got for delta 1 here by means of this two-stage argument to work out d delta by dA at constant p. Then you use another little bit of physics. There's a minimum energy condition which tells you the value of P1 minus P. And what you end up with is this formula at the bottom. Pi is equal to something, various numerical factors. It's got a W in it, it's got a K, the elastic constant, and it's got an A to the 3 halves. And that's what this gives you. So, that, if you like, is one proof that the effective force is not proportional to the contact area. The next thing, I've tried to word this talk in the form of statements which are perhaps slightly more interesting than it otherwise would be. I picked up the points which those who have not met fraction mechanics idea might be surprised by. This one not particularly surprising, but sometimes overlooked. Attractive forces do give you a bigger contact area than you would if you didn't have any attractive forces. And that's true even if the only type of deformation you've got is elastic. In the elastic case, using the notation of K instead of E star, the formula you met this morning comes out as KA cubed over R is equal to the load. Well, all you do, can I just have a slide projector on, please? The next slide. A and R that was derived by Johnson, Campbell, and Roberts in 1971. And there it is. I haven't actually written it down because it's rather complicated, but all we've got to do is to take the last two equations and substitute for pi. Let's work out a very simple example. Paint again, rubber particles in paint, emulsion paint. When you put the paint on the wall, nobody's going to come along and apply any external load to push the paint particles together. They've got to stick together of their own accord. And you don't want it to be porous. Therefore, let's ask the question, how small do those particles have to be for W or pi, whatever you like, to cause complete coalescence? And so I put P equals 0, and if you substitute in the JKR formula with P equals 0, you just have Ka cubed over I equals 2 pi, and that comes out that R should be less than numerical factor times W divided by K. Right? So if all that's involved is the elastic constant and the adhesion energy. Right, another statement which I put in a box is that we are at last getting down to the something that might be useful in the next few weeks. What I'm going to talk about for the next minute is a situation where I'm not concerned with what the mechanism of friction is. It could be due to something completely unrelated to adhesion. All I'm saying, I'm making exactly the same point, in fact, that Daniel Moshe's made in the question today. Namely, that if you've got something that's behaving according to the JKRS model, or at any rate is responding to surface forces, you're going to get a bigger contact area than you would otherwise, and this is going to change the friction behavior. And the result is that the friction force may vary non-linearly with load. You might think that it was enough just to add the attractive force onto the external force and multiply by mu, but that turns out to be not the case. And I've just put one or two notes here. Supposing that for some other reason the force is proportional to the real area of contact, and let's suppose that the real area of contact is proportional to the load. Professor Tabor talked briefly this morning about various reasons why that might be, and Jim Greenwood will be telling us more about this later. Then you might think, and there is some experimental evidence, that we should replace load by Ka cubed over R, and redefine the friction coefficient. If you could define friction coefficient how you like, it's logical to define it in some way that gives you a constant quantity. Define it so that it is constant. In other words, so that the force, frictional force, is proportional to Ka cubed over R. And the result is that you get a three-term friction expression. You have a load term, you have a surface attraction term, as I got at the top of the slide, but you also have a cross term because the attraction itself depends on the load, as I have shown you. The next point I want to make, appreciated in the 70s, is that in a sense it's the analog as regards plastic deformation of what I've been talking about in connection with elastic deformation, namely that even if you don't apply any external load at all, you can still get plastic deformation. And that diagram there, very schematic. I've got normal load P coming from above. Those arrows indicate the directions of the relevant forces that are acting on the upper of those two bodies. I've got two bodies in contact. That obviously will be in equilibrium, there will be equal and opposite arrows acting on the bottom one. If they act on the top one, there's the normal load acting on it from above, there's the intermolecular attraction acting around the edge, pi, and there's some kind of compressive reaction at the center to give you static equilibrium. This is an example of a size effect. Whenever you need fraction mechanics, you always end up with size effects. The force required to produce plastic deformation in the simplest case will, for example, be proportional to the area, won't it? to imagine a material of constant hardness. You double the area, you double the force needed. Reduced plastic deformation will be proportional to A squared. And by the way, I'm just talking about the initiation of plastic deformation. I'm not talking about full plasticity. Pi, as we've seen, is proportional to area to the 3 halves. And therefore, if you go to smaller and smaller contact sizes, both the force required and the attraction force they both get smaller. But the attraction force won't get smaller quite as fast as the force required to initiate plastic deformation. And therefore, provided you go to a smaller contact area, you're bound to have some plastic deformation. Now, the proper calculation has been done by Burnham and Robbins. The stress tensor has been calculated. The diagram is different, but of similar form to the diagram that you saw for Hertzian contact this morning. If you want a very simple approximation, here it is. P plus 1.5 pi is equal to 1.1 times pi a squared times the yield stress. And if you do the similar sort of calculation as I did for the elastic latex particles case, if you put the load equal to 0, then you get another condition here. If the radius of contact is smaller than that expression there, then plastic deformation will be initiated. There's a K there, it's K squared this time, there's a W, and this time there's a yield stress, of course, comes out as Y cubed at the bottom of the fraction. And also, the same kind of sum has been done for the condition for fully plastic deformation to occur. Could I have the next slide, please? This is an example of a map, a deformation map. That's it. It's too small. You'll have to look at the poster afterwards. Let me just make a point that along the x-axis you can plot adhesion energy. It's normalized, in fact. It's normalized with respect to K, R, and Y as well. Up the left-hand axis, you have the radius of the contact region. And a diagram of this kind, which as I say you can look at afterwards, can be drawn for 0 load. If you're in the bottom third of the diagram, everything is elastic. You have the JKRS equation. If you're in the upper half of the diagram, you've got full plasticity. And if you're in the middle, you're in the very difficult region as regards calculations, the elastoplastic region. And you can work out the conditions for a particle of a given size to cross the boundary. If I take a particle that happens to have this particular energy here, and I put the two surfaces together, then I shoot up the diagram until I reach the equation, which is this line here. And as I shoot up the diagram, I cross this boundary here, plastic deformation is initiated, and I grind to a halt at this point. So these diagrams can be used to predict what will happen. And if you take, for instance, if you take gold, let's take clean gold, W2.4, it turns out that the radius has to be smaller than 5.8 millimeters for this transition to occur. And if it's contaminated, then obviously the radius has to be a lot smaller. The evidence for adhesion-induced plastic deformation is of two kinds. One type of evidence, or more than two I should say, but there were two I'll mention now. One type of experimental evidence is from the very nice experiments which you'll hear about, I'm sure, from Professor Turlin on Thursday evening, where he put tiny metal particles in a container which allowed them to coalesce and used a transmission electron microscope to examine what had happened. Another type of evidence is in connection with the kind of experiments that we've been doing at Lancaster for some time, taking an ultra-high vacuum apparatus and doing a micro-contact experiment under conditions where we can obtain single asperity contact to get around the problem of contact between extended rough surfaces. And by doing experiments of that kind, there's semi-quantitative agreement between maps like this and experiment. The limitation, of course, is the fact that we're using macroscopic concepts such as yield strength. Right, two effects that describe the importance of roughness in connection with adhesion. I'm actually up to time with that here. Roughness is the topic of Dr. Greenwood's lectures on Wednesday, but I'll mention it briefly here. The reason why I say that at first sight, if you've not met this idea before, they are contradictory, is, as I've written there, if you're gluing two surfaces together and you really want them to stick, you roughen the surfaces. The example is, for instance, supposing you have punctured the tire of your bicycle. You take the tube, and it's a good idea to use a bit of sandpaper, emery paper, to roughen the tube before you stick the repair patch on. That's what it says on the inside of the box. It says roughen the tube before applying the glue. On the other hand, second point, the two surfaces that are placed in contact, roughness greatly reduces the pull-off force. And again, what you do after you've struck the repair patch on your bicycle tube, the patch tube, you don't want it to stick to the inside of the tire itself. And so what you do is you roughen it by dusting it with chalk before you put the tube back inside of the tire. So that, if you like, is an illustration of these two effects. And in 1975, Fuller and Tabor analyzed this phenomenon in terms of the JKRS description. There I've tried to show the situation of, on the left, we've got a couple of asperities which, although in contact, were relatively short ones. And so, in order to touch, the intermolecular forces have had to stretch them a bit to make them touch. So that's why I've written the shorter asperities are stretched, and it's those asperities which are responsible for the surfaces being pulled together, and the force there is roughly proportional to W times R. On the other hand, the two asperities that I've got on the right, they want to overlap. They're longer ones, and therefore, in order to reach equilibrium, you've got to compress them. So they become like compressed springs, tending to push the surfaces apart. And so it's this variation in height of the asperities which is responsible for that. But it's very difficult to observe any measurable pull-off force with rough surfaces. The criterion I've written there is a question of whether or not WR is much greater or much less than the function that I've got on the right, which involves, as well as K, it involves R and the standard deviation of asperity heights. It's not the asperity height, it's the distribution of heights that's important. If pull-off force includes ductile contributions also, you can still analyze that. It turns out that a parameter of importance is W divided by H times sigma. W and sigma as before, H is the hardness. And the value of that parameter determines whether or not we get instability. If we get instability, we'll get more plastic deformation until finally equilibrium is reached. And the consequence of all this is that, as Dr. Adams may possibly mention, he'll be talking about the friction of granular materials on Thursday evening. By analogy with friction in some sense, it turns out that if you apply this roughness criterion to hard ceramic particles having typical values of radius, adhesion energy, and sigma found in practice, the prediction nearly always is that the pull-off force you observe should be completely negligible. But in practice, fine particles of various materials like aluminum oxide, titanium nitride, and other hard materials can indeed display strong adhesion. And it could be that a different geometry altogether may be involved. Could I have the next two slides, please, one after the other? That one is a kind of rippling effect that you get if you clean a surface by ion erosion. So that type of surface is well taken care of by the Fuller and Taylor description. If you look at the next slide, you can see that what I've drawn schematically there is a kind of terraced surface following, to some extent, the same spherical flat geometry that I talked about before. But you could imagine a situation where, because of the atomic structure of matter, where you had atomically flat terraces separated by steps, one or two atoms high. And in that particular case, it could well be that a different description altogether, that the effect of roughness on adhesion is required. You can see that if you've got that geometry, then if I apply load and bring the surfaces together, we have the kind of situation where the effect of the steps is at the periphery, is to hold the surfaces apart at a separation greater than the separation which corresponds to the maximum value on the force distance curve. So that's the kind of thing that perhaps needs to be analysed and has been to some extent. Here we have another topic that may be related to this possibility of the importance of some kind of stepped topography. I don't think I'll say anything about this. I'll just put the slide up so that you can see what it is that I thought of mentioning. The reason why I'm not going to say much is because, firstly, I raised the point this morning anyway, because it seemed to me that it was related to what Professor Taylor was talking about in terms of elastic energy as well as surface energy being involved when you separate the two surfaces. But, well, let me see. There's the statement. John Franklin may not agree with the form in which I put it, and I'm sure he'll be talking about that effect next week anyway. The thing is, there is some experimental evidence that you can get a sudden jump to contact in the sense of an abrupt establishment of a finite contact area. There are really four kinds of experiments that give that evidence. There are STM and AFM experiments. There are experiments of the type using fine probes in UHV, which I mentioned before. And then there are molecular dynamics simulations. And the possible causes, this again is something which I'm sure other people, as well as I, will be bringing up later on. I've listed them there. There are causes that involve competition between the different types of energy that are involved, the cohesive energy within one of the lattices and the adhesive energy describing what's happening across the interface itself. There's also the effect of geometry, which Professor described. And then there's the same adhesion-induced plastic deformation that I mentioned. Namely, if you touch two surfaces together, you have a certain amount of surface energy released, clearly, because you've got less surface area than you had when you started. And you can work out the conditions for this to be converted partly into plastic deformation. And that may help to give you this enlarged single crystal junction. Right, the last major topic that I want to mention is this one, because there is an important concept in friction that is more or less exactly parallel to this one. And that is, the lot of force we get in practice, in many cases, is very much larger than what we would get from equilibrium fraction mechanics. There are various ways of calculating values of pull-off force, and in fact, there isn't really any need for me to go into this because it's not directly relevant to friction. I have information on that if anyone would like it. I've not talked about that today. quantitative point, though, that although the theory is not bad, and you can have maps, rather like the map I showed you for adhesion-induced plastic deformation, there's a corresponding map predicting what the pull-off force should be in terms of various material parameters involved. The point I want to make is that to make experiment and theory agree in any way, the values of W that you need are very large indeed and show at once that energy dissipation mechanisms have to be thought of. And there's an analogy that I've written there. On the left, let me take the one on the right first. The very important point that very often the energy dissipation mechanism is a bulk mechanism. It involves significant viscoelasticity of one or other of the materials that we contact. And the surface forces can trigger bulk energy losses. And the result of that turns out to be that the pull-off force is very large. And the analogy with friction is that often you get bulk energy dissipation, which leads to a greatly increased friction force, but you need some adhesion to trigger it off, if you like. So that's why I've put that often the adhesion term in friction, or the tangential interaction term, whatever you like to call it, is far too small to account for the observed frictional force, but it can trigger a large increase in the plastic strains involved in pi. And this was pointed out very clearly in 1981, I think it was, by Professor Johnson. So let me take up then this point on the right, that surface forces can trigger bulk energy losses. There is an expression that is taken from the paper by Moderator and Burnham. What we got on the left is a kind of driving force for the inward propagation of this peripheral crack that I mentioned. G is the rate at which strain energy is released, not rate per second, but rate per unit crack area. G minus W, in effect, is the force tending to drive the crack inwards. And on the right, we have the drag. And the drag is actually proportional to W. It's proportional to the adhesion energy. It's also a function of the velocity. It's a complicated function. I put 0.6. It isn't always 0.6. It can be some other function. There's a function, AT there, which is going to be talked about possibly tomorrow evening by Dr. Majus himself, or on Thursday morning by Dr. Briscoe. They will be talking about viscoelastic materials. So I don't need to say any more about that now. The drag arises from the fact that there is hysteresis in the cyclic variation of stress undergone by an element of volume near the tip of the moving peripheral crack. And I've put down a note there about one of the various models that's been used to describe it. And I'm sure that there are similar effects taking place when individual contacts are being broken during sliding contact. Another energy loss mechanism, nothing to do with viscoelasticity, again, comes back to these nanometer scale stepped surfaces. Imagine you're doing one of these single asperity contact experiments that I mentioned. Thanks, it's just the slide. Let's plot contact area up the y-axis as a function of load on the x-axis. You get a lot of individual contact experiments, if you like, as you compress, as you increase the external load, and each of those terraces comes into contact with the opposing surface. You get a lot of individual increases in area. But when you come back down again, if you do a cycle and reduce the load, it won't follow the same curve, just as when you take a single sphere, which is in touch with a flat surface, and put it off again, you get hysteresis. So that, if you like, is another hysteresis mechanism, which may or may not be relevant. There are two topics which ought to be talked about here to complete the list. They are the possibility that some materials, such as titanium nitride, thermal activation is required to get adhesion. In other words, you may get very strong adhesion if you can surmount an energy barrier. Then there is the whole question of friction of a type that does depend directly on adhesion, such as has been described by Dr. Savkoor in his paper with Briggs in 1973, was it? And recently by Thornton in the extent of this moment. So I think I'm right that we will probably be mentioning this tomorrow, so I won't say anything more about that now. And I have I finished?
We've got about a minute and a half.
I'll stop. That's it.
I should say that we have thanked the speaker for a very fine speech. I forgot to mention the introduction. Right.
You happen to have a transparency.
How do I say?
There was some talk this morning about the role of auto-adhesion in definition of friction force, and Hubert brought it up a little during his talk. And what's shown here, it's old data, it's the frictional force in micronewtons against the applied load in micronewtons for two 20 micron no polyethylene terephthalate fibers. We drew this, well, Hubert was talking, but I was listening. There's the contact configuration. You can apply the load by bending the fibre, and of course if you move this fibre backwards and forwards you can displace the fibre. Simple beam equations will allow you to compute the friction, or indeed if you measure the critical separation here with respect to that axis as a function of L cubed, you can get the autoadhesive load, WC, that's what you mentioned. And I use Johnson.How and Robbins there, and I've shown this scaling disparity argument. Now, the reason I bring that up is that you can actually slide under negative load, and you can see the load is negative there. That means that if you plot the coefficient of friction formally, then it follows this, goes to plus infinity, then comes back from minus infinity, and then to a point there. Now, this thing here, alpha, I'll come to that in a moment. Now, when I object to Kevin Kendall's analysis, which you mentioned, and here are the equations, what you would like to do is to use the adhesion model of friction, and there's this interface shear stress, which Singer will talk about a great deal later. Kevin Kendall didn't have that as a function of contact pressure. That's alpha. It's also this alpha here. So if we combine this pressure-dependent shear stress with an area of contact, and I just wrote the Hertz equation here, I put the effective radius of curvature in because of the scaling of asperities. That can come from here. Now the point I would like to make is it's not necessary to do this convoluted argument that Kevin Kendall did. You can just add the WC, if you don't mind the phraseology, to the applied load and combine it with this term, and that solid line is in fact that fit. Now what Kevin had to do was, because he didn't include this pressure term here, he just had a constant in there, he had to get another term in here, and that's why he prevailed upon you, I think, and others to believe that that was a better analysis. Now can I just finish by saying this alpha here. Professor Dowson mentioned pork fat this morning, did he not? Yes. Pork fat. Marine slideways and Coulomb. Yeah. Well, if you transcribe these relationships, you can write the coefficient of friction tau naught, that's that parameter there, upon P, that's the mean contact pressure, and that's alpha. Now, of course, when the contact pressure is high, as it would be on a marine slipway, this term is small compared with that. So U tends to alpha. And someone, it wasn't me, chose to measure the pressure coefficient of interface shear stress of pork fat. So he could compute the upper limit of the coefficient of friction from this curve here. And it turned out that the coefficient of friction that Coulomb had was, I think it was about 0.3, and the pressure coefficient of pork fat thickened with lime, it was thickened with lime, was about 0.27. So the point I wanted to make was that it isn't necessary to account for this autoadhesive load component via a convoluted argument. You can just simply add it, and I think quantitatively that's correct. This form then follows the classical form, mu going to infinity, and then coming back from minus infinity. You're quite right, the better thing to do would be to define mu in such a way you didn't have these anomalies, but in interface adhesion models it's really difficult to find a way because it'll always follow that trend.
I accept entirely what you say, Brian. The point really is whether there are really two quite different physical effects here. If the contact area itself is also increased as a result of surface forces as well as the external applied load, and whether the shear stress itself is a constant, or as you have shown in this particular case, whether the shear stress itself is pressure dependent. So could one not have a situation where both effects are occurring simultaneously, in which you have an even more complicated situation?
I think the pressure dependent in most cases.
Well, that's something which you've shown by experiment in this particular case that it dominates. But one can imagine other situations where that wasn't necessarily the case. I mean, there are even, you can get into trouble if you start using multi-spectral arguments because you've got to make sure that the whole is consistent. But at the first sight, I would thought that you have a case where for reasons of multi-asperical contact, the contact area is proportional to the load. Then this effect that I mentioned this afternoon could still take place, even if the shear stress were a truly constant quantity and hence zero pressure dependence. I may be wrong, but that's what I would say.
Any other questions, comments? Yes.
This is a question about friction transmission to the negative force produced by adhesive forces. How do you square that with the Savkoor rings picture of the when you superimpose tangential tractions on normal pressures, this progressively breaks the adhesion and the contact area reduces back to what the estimate suggests? There's a conflict there which I can't resolve.
I wonder if, could I ask Irwin Singer whether he would like to say something very briefly about that now or tomorrow, perhaps? Because I wish I knew the answer to that question. It would be marvelous if we could find the answer to that question this week sometime. I don't want to start confusing the issue really by speculating on it until he's spoken. Is that how?
I think this is extremely important question, and in fact, connection to what Hubert Pollock said, and also what Briscoe said, we did specifically a lot of experiments, and in these experiments, what we tried to do was to use flat-faced cylinders instead of spherical surfaces, because spherical surfaces tend to be very difficult to control because the geometry and the loading makes the contact area change. It's also a little unstable because you can get peeling on asymmetric peeling with only a small moment. So what we did was to make experiments on flat cylinders, optically smooth flat cylinders, and with a very special sort of silicon rubber which could also be made optically smooth. And we could establish this effect much more, let's say, firmly. I have a lot of results on that, and also, but unfortunately, they are not landing for my lecture tomorrow.
discussion workshops for this.
Nanotechnology showed a slide this morning with some friction coefficients. I think maybe it's low. Has something to add on?
All right. Are there any other questions? In that case, let us take a brief 10-minute break or 5 minutes.
Which surface? The nickel and the gold?
The hexadecane would be on the line surface.
Or you're asking for the
metal surface lattices, how are they?
16%. The gold is larger, 16%.
What's the angle between the two metals?
In the case of nickel and gold surfaces, no angle. There's no metal here yet. This is the gold, this is the alkane. I'm going to bring the metal. So now we bring the metal down, and the first thing that happens is the bulging of the alkane. This is very important for dipstick measurement. We want to use that optical microscope. People have done that. IBM and Almaden, Formula and Mate have done. Here's the nickel tip, here's the gold. I'm sorry that they don't have, well, viewers, the color slide will not be helpful today. Here's 17 angstrom. This is 17 angstrom distance here, and you see the wetting of the bottom of the nickel tip by the alkane. The force at this point is minus half a nanonewton. Very small attraction. So this stretching of the string. As a matter of fact, we have not done the full analysis. They say not for David Lutkin, who didn't sleep a few nights, and I didn't sleep because I wanted to see the results. He didn't sleep because he made the results. And so we don't sleep for different reasons. But here's the well, we can calculate the meniscus is caliber radius. For those of you who know what I'm talking about, this is the interesting stuff. Now you start pushing it. Now you start lowering. So I'm bringing it down, and now I'm bringing it to a distance of 9.5 angstrom between the bottom of this to the top of that. So between nominal, the bottom of the tip to the top of the surface. And now you see that the material ordered itself into very definite 2 layers. And anything else is around here. The force is now repulsive to nano. At this, we bring down even further. I marked by in red the bottom layer of the nickel tip because it's here 6.5 angstrom. The force is 0. Just cancel itself out. 0. Now, if I lower it down by another 1.4 angstrom, I get the tremendous repulsive force, 25 nanonewtons. And notice that I start to deform the gold surface. There's only one layer now, one layer of hexadecane trapped, basically crystallized under this thing. And there's a very large repulsive force with a deformation. As a matter of fact, we were early in the morning where David told me he didn't want to work for this meeting. We knew that it was sooner or later because we not do it. But we wanted for this meeting, and then one alkane molecule went to the top of the other, and all the pressure concentrated there. This unfavorable signal across. You start to lower the tip very slowly, but one molecule got trapped over the other. And we wanted a more ideal test for classical example. Things won't have a test cycle, the alkane might. Now, something very interesting happened at 4 o'clock in the morning. And what happened was, assisted by the formation of the substrate, this one warmed itself out. This is called Brow's diffusion in the language. That's a formulas. And what happens is the following: that here's an alkane molecule, and here's another line in this loop on top of it, and here's the substrate. And this molecule, the one with this finger, started to warm itself by taking this gold atom here and making it into an interstitial in the middle between the first and the second layer, and the alkane, the carbon moved here. And then the next one did this, and so on, and it each itself out. So it's assisted by the substrate, and we ended up with a very flat, nice monolayer with very large repulsive pressure. But then we pull it a little bit lower, and then lo and behold, something happens. So you see, at this distance, by the way, this is coming close to the Johnson compass. Remember, 4.25 is another Johnson compass. Well, we brought it to 4 angstrom, and let me explain this picture. What you see here is all the atoms in the system: gold, nickel, and alkanes. Here, I just show you the gold and the nickel, without the alkane, the metal only. What do you see? That there is Johnson compass. Namely,
when you push it enough, the alkanes, as much as they are trapped, they cannot withhold this pressure, they cannot contain it. And the node is pushing them out, but not all of them. At this distance, the force before was very attractive. The force now is only -5 nanometers. At even larger distance than that, it was before something like -40 nanometers. So you get a much weaker, if you want, much smaller attraction to the surface because they're screening or there is steric inhibition by some alkyl molecules. As a matter of fact, if you look down on this thing, I will not go into detail. This is some of what you find. This is a picture here, for example, what happens right under the pit. This is the whole of all the molecules above. So you see the first layer, you see ordering under the pit. So I did expect something else. I didn't think that it will actually freeze and it will never jump to contact, but it does jump, although there are some alkanes. So in other words, metal atoms do adhere to one another, but they're interlaced with some alkyl molecules. Very interesting. Let me almost close here. I will, I guess I'll close it totally in a minute. And just tell you about one more thing, because I thought that this is appropriate today, since this was mentioned here. Well, I will show you just this thing here of stick-slip phenomenon, and then I'll just and this is to do with calcium fluoride that I mentioned before, and this hysteresis. We did these experiments with calcium fluoride. It does happen with this material. This is the hysteresis of calcium fluoride did against calcium fluoride surface. Lowering, bringing it here to a pulsive force, and then lifting it, and you see hysteresis. Somewhat smaller than before. But then we did something else. We slided it across. And when you slide across, something very interesting happens. This is the force in the x direction against the displacement in Armstrong here, as I take this calcium fluoride tip that is mashed into that nicely, and I'm starting to move it along. And as I move along, you see that the force goes from being very attractive to slightly repulsive, and it oscillates like that. Okay? And this is exactly a stick-slip phenomenon. Let me show you actually the atomic configurations. Notice which atomic configuration I'm going to show you. A, up, B, C, D, E, F. So let's look at that. This is the A, this is the calcium fluoride tip, this is the substrate, here's the tip. These are the calciums and the fluorides, the dark atoms in the color. Right, that thing, but that's the calcium, these are the fluorides, the big atoms. This is point B. You see, we are moving this whole stage here. These atoms remain stuck. And now if you follow this thing to the end, you see that you actually, this part remains stuck to the surface, and this thing there, so you've got actually a decent wear. The wear particle made of 3 layers. 2 layers of fluorine, and in the middle is calcium plus 2 fluorine layers. So that's the stick-slip phenomena is the motion of one atom at a time. That's the phenomenon. If I look on the temperature here, the progression of energy, what I will see is that after every one of those transformations, there's a lot of progression energy in the case. I think that with this I will probably stop, and I think that I gave you at least the feel, although not in completeness that I wish to the degree of detail that you can learn from these things, and the ideas that it gives you with regard to what processes are possible. What I didn't have a chance to do, and I hope that this will actually be a theme that I will personally benefit here, is to try to relate these things. We have contours of these shears and the like, to relate that to known modern theories in continuum contact mechanics, and perhaps we can somehow join together by perhaps helping us to design new computer experiments to clarify some of the mysteries of this theory. I might start off with a comment that modern man's two of his greatest joys are television and computers, and food and No, we didn't for a simple reason. We wanted to last result, not something interesting. And it's still interesting. The non-wetting out is the same to do. No, we haven't done that.
Are there any questions? Yes.
Uzi, would you return to the graph with the nickel gold on the contact and then the nickel chip with the gold layer? Okay, you've got essentially you can find out what the difference in area is of the two currents. Right. Have you related the difference in area to, for example, the bond's energy per atom?
No, we didn't, but it's not this, obviously. You see, by the way, so this will take a lot.
Uzi, your simulation runs, each step is a few femtoseconds, right? And so the whole thing is sort of over in much less than about a nanosecond, maybe.
Over each thing.
From the beginning of your run to the end.
Now, I run at each stage. Each stage is allowed to totally equilibrate for whatever time it takes. So don't associate any lengths of time to the process of lowering and bringing up. I do not do rate-dependent studies here. I try to do this as slow as possible. Namely, we wanted to go to a succession of quasi or equilibrated states because the experiment is done so slow compared to anything that because the experiments are not on a nanoscale. So you see, I did not move continuously the single second speed. I could move it, but I stopped, then move it slightly more, and totally allow all the atoms to find the equilibrium position, and lower it again. So it's actually, it's a canonical sample. It's constant temperature, isothermal sample.
But it's not a real thermodynamic equilibrium. But if it were, the system should be at any point a concentric sphere of nickel and gold.
Because we would live only once, right? And it would take forever.
I don't take forever, but I'm telling that your equilibrium is, I don't know, maybe mechanical or thermal, but it is it's just one which is long.
It is the practice.
It's not actually
it is the practical equilibrium. There are, in principle, the system is a product which is in all phase space. And it will end up with time we have to.
The question here,
This is really on your, you said that an important effect in our interaction meeting like this was to bring together this sort of work with continuum mechanics. You impressively showed contours of hydrostatic stress and the local areas of hydrostatic tension at the edges of the contact. That's consistent with continuum ideas. But in order to make these comparisons more effective, we need to know the deviatoric stresses as well, the shear stresses. Is there any difficulty in principle
No,
providing that information?
No, we actually published some of it, so I will show you exactly. No, we have shown pictures of deviatory stress. It's very easy operation with computing, with some practical means. And then take the deviatory stress. And yes. Well, in most articles, in the science article and in the other one, I believe this is, for example, the deviatory stress. This is the deviatory stress. Nickel gold, and this happens to be the square root of J2.
Under the road? Under what road?
On what road? This is on the way up, and this is a particular stage of the no, the question was, can I in principle, and can I get information out of it? And the answer is yes. I'll try to make that clear in the. I think that's an important question. In the workshop on molecular dynamics, I think we will explain in detail how you actually calculate this thing and how you analyze that. It's possible, because knowing the position, I can calculate the whole stress test, and then
waiting for things to settle. But if Jacob's question is, if there was something happening on a 1 microsecond time scale, would you see it? Then the answer has to be no, even though there might be some 1 microsecond time scales that would be relevant to the experiment. What one typically sees is some decay of changes, and one hopes that that's the final state. But in nature is not always so kind. We're still not at the level where simulations control microsecond time scales. Something is important at that scale.
Yes. Now, if there's something that could have happened here on a microsecond time scale, an relaxation process that goes on a microsecond time scale, but since I'm going to a succession of very small changes, starting from non-interacting to interacting, I think that the relaxation processes that are more than several decades of vibrational frequencies are not going to be real. I don't know.
They may not be.
If there is something, yeah, I cannot speak about that now.
What do you move when you do your experiment?
I move the holder over here, the canopy. There's a static, there's a nickel here, and there's a dip here. And the whole, this thing is moving out.
The holder atoms, they're attached to when I'm out vibrating.
No, the whole atoms
So we would never do. We never do would take the suggested to hold the top again. It's only attached to the holder.
he didn't suggest it for any particular one. No, it could. What he says is that if it jumped to content, so he jumped. Could. That's what you said. That it could visit this stage, or it can also go back.
Erwin Singer, Naval Research Lab.
Remember what you said.
Uzi, can you give us some examples of stress-strain contours you've generated which don't really square with any of the concepts of Hertzian mechanics?
Oh, this one that they showed actually.
Right. Can you say something about it? And for example, if you add things like JKR or try to compare it, can you tell us in what regimes we have to be careful in applying it? Or
I cannot tell you this yet in that detail, but what I tell you here is that this morning Professor Johnson showed the principal stress Taiwan, I think it called it, sigma XX minus sigma CZ. You showed pictures that look very much like what I show as hydrostatic pressure. That's the reason I asked you to show the hydrostatic pressure. Well, that's one thing that doesn't seem to be true. Or maybe I...
Depending on the level. That should get to the bottom. There was no adhesion in that picture that I showed, and it was with a high normal load. The one we showed a moment ago with strong adhesion and a tensile load, that was just what I would have expected.
Okay, so...
It was all plastic and plastic.
Oh, the next up. No, this is the slight indication. The next up, the next up we agree on.
This seems to be a lively topic still. I want to raise in just a minute, but I'll take a last question from someone who hasn't opened his mouth yet today. Is there any such person wants to speak?
What sort of temperature are you considering in terms of lighting? That's to say, what is the effective temperature of mobility of the applicants? Is that an important parameter of the second law of the
The temperatures at all these experiments that I've shown you in the slips were 300 degrees Celsius. There is a strong effect on gold. As a matter of fact, once we have done this thing, it turns out that there are very clever atomic force spectroscopists who think how many very sharp tips. Probably if you come down and put it out, it's very sharp. Calculated in Stanford will start doing that. Very, very nice sharp tips. However, he found it too short. So he's going to be raising the temperature
for this opportunity to spend a few minutes with you this afternoon and to discuss a subject which has come up several times before in this meeting and which will undoubtedly come up again as the week goes on. Now, I'm an experimentalist primarily, not a theorist. However, I still feel that there's still a considerable amount to be gained by doing relatively simple experiments in friction. And by simple, I mean they may be simple to do, but not necessarily simple to interpret. The experiment I'd like to discuss with you this afternoon is a relatively straightforward one, and it's a subject that came up actually at dinner on Sunday. And that is, suppose you had two materials, and you put the same two materials in three different machines, and you use, say, oscillating motion. Would you necessarily expect the same frictional behavior if friction is indeed a property of the two materials involved? Should you get the same value in several different machines? Well, before I get to that, by means of background, it seems to me mapping is quite a popular subject now in tribology. We see wear maps, we see friction maps. And in the map of the world of tribology, perhaps there might be a place for the Blau, or the friction forest. And if you'll permit me the analogy of the forest and the trees, the friction forest is a rather unusual set of trees. They vary considerably in size, all the way from atomic scale to the size of geological plates that move about under the surface of the Earth. And many of us look at this forest from different perspectives and have our own favorite rows of trees. So finally, right. Well, let's take a look then at some of these phenomena which might occur at different scales in either friction or wear. And if we start down at the bottom end then, we can talk about atomic diameters typically. I'm plotting here a lot of size in meters. And then as we go up in size, we might reach the thickness of an iron-implanted layer. Still higher, and we might reach the size of the dislocation cell, and that might be characteristic of a sharpened dislocation cell which results from shear during sliding wear, perhaps 100 nanometers in diameter typical. And then if we go still higher, slightly higher, we get to the size of mild wear debris, and Charlie Yust at Oak Ridge National Laboratory has spent some time in a transmission electron microscope looking at the sizes of wear debris for ceramics, and we see 80 to 100 nanometer diameter particles, which are typical as size. Then we go up surface roughness, perhaps 0.02 to 0.04 microns for polished surface, thereabouts. Sizes of solid film. And then on the left side, if you do micro indentations with a Newton indentar at 1 Newton load on polycrystalline aluminum, they have a micro hardness of 23 to 28 gigapascals. You get indentation depths of the order of a micron or so. Go up to pure copper, still less, greater depth. Then you work your way up, Hertzian contact diameters, and then the scale by no means ends at 10 to the minus 3, but for laboratory pin-on-disc wear experiments, we might see wear scars the nominal sizes, the order of 1 or 2 millimeters in diameter, typically. And then, of course, you go above the scale and you get to all manner of industrial applications, mechanical face seals with steam shovel bucket teeth and so on. But a lot of the phenomena that we're interested in probably occur within this range. And before I leave this, it's interesting that some of the nominal pin-on-disc type wear testing machines produce areas up in the minus 3 to minus 4 range, perhaps a little larger. And then we have some devices which are rather finely tuned, very small contact area, low load, in which we might approach some of the tens of microns. And I'll be talking about the friction microprobe shortly. We're going to be talking about between about 2 and 15 micron contact size. down here we have the atom probe type instruments. And in such, I'm looking forward to hearing about those next week. But it seems as though there are a few decades of size scale in which people are not applying instruments that have characteristic dimensions of contact within that size scale. And I think there's still some work to be done in bridging the gap between the more macro and the more nanoscale. I probably should have put on up in here the typical depths of nano indentations. However, for friction, we may need other instruments besides nano indenters because they were mainly dealing with faceted diamonds and so on. Right. Now, I say the relative contribution to friction depends on both the imposed conditions and on time. So if I'm going to use another schematic viewpoint of things, perhaps when we have low normal load or low contact pressures, we might be able to sense the effects of pristine atomic layers, or perhaps even initial surface contaminants that would swamp those effects. And as we increase the contact pressure or the load, we may be able to sense the effects of depletable surface films. And then initial surface finish and texture may begin to influence at still more severe conditions the initial microstructure at this point. And then when we get to rather high loads and contact conditions, we're beginning to then deform the material. The deformation of the material may change its shear properties and may then affect the friction. However, what's not shown on here, and which is probably just as important in the most high load conditions, is the effect of the machine. And I think a lot of the mechanical engineers sitting in the audience may recognize that there's more to this tribo system than just the materials involved. And especially if you've got a high amount of shear forces transmitted, you can stimulate the machine. The machine may oscillate and feedback to the contact, and you have to consider this feedback loop as part of the process. And maybe materials people aren't used to thinking about such things when they model friction. Now, I said we had the same two materials tested on different machines. So in order to characterize the materials, I used stainless steel type 440C. Its composition is shown here. But I want to point out that the microstructure contains fine carbide particles, perhaps 1 to 8 micrometers across, blocking carbides. Spaced maybe 2 to 5 micrometers apart. And these sorts of dimensions are characteristic of the friction probe experiment that I'm going to describe shortly. So that we may have particles within the microstructure that are about the same size as at least the elastic contact. The flat specimen material was an alloy of nickel and aluminum based on Ni3Al. It's essentially a single-phase polycrystalline material. It has a face-centered cubic crystal structure with nickels having a preference for the face-centered positions. It has some rather unusual properties, but all I wanted to do was identify the two materials that we've been testing on 3 different machines. Now, the first machine, which we call friction microprobe, uses 1 millimeter diameter spheres. Normal force varies from about 10 to 100 millinewtons. The sliding velocity about 10 microns per second, and the typical stroke length in this oscillating test is 100 micrometers. The second was more typical of a bench scale laboratory reciprocating tester, pin-on flash micrometer. Sphere diameter here larger, normal force from about 1 to 10 newtons. Sliding velocity, this is an error in both cases, it should be 100 millimeters per second, so that there are 4 orders of magnitude different average sliding velocity between that and these other two. And then finally a Cameron Plint TD77, which is a rather husky reciprocating wear machine. And here we explored the load range between 10 and 100 newtons. What's also significant about these machines is the way we measure friction. And I want to take just a minute or two to explain that, because I think the manner in which you measure friction has an effect. With the friction microprobe, we measured friction by taking the output of an amplifier and just putting it straight on the analog signal straight into chart recorder. And we checked this by looking at the same information with a digital data acquisition efficient system, and we didn't see any significant details at much higher frequency that we saw, other than we saw in the chart recorder. With the pin-on-flat turbometer, we used a digital data acquisition system in which we measured the friction values at a rate of 1,000 per second. And we could play them back and observe the details of the friction trace. With a commercial wear tester, they have kind of a funny way to give you the friction coefficient. Since it's moving back and forth rather fast, they electronically rectify the signal, take the root mean square of that, and then they plot that out on a chart recorder so that they don't overdrive the chart recorder and it can't keep up. So when you look at friction recorded in that way, you might get a slightly different picture of what's going on. But nevertheless, let's take a look at what the friction microprobe design is. Essentially, we have an aluminum boat, and at both ends of this aluminum boat is a web, so it's a spider-like arrangement. And there's a capacitive sensor at the left end looking at one of the webs, and we then calibrate the air gap with the amount of displacement, which is elastic displacement. We also have to compensate for the position of the ball. When we drive then the whole thing back and forth, and we can also lift up and down the slider so we don't have to touch the machine. It's on an air suspension system, so we minimize the vibration. Well, before I do that, I'm giving away the show here. I want to talk a little bit about the construction of this intermediate device, the pin-on-flat thermometer. The head here, this is the plan view or the top view. We would have the pin at that location and the dead weight on top of it. Now there are two dowel pins, and they're feeding through recirculating ball bushings. So there's a little bit of slop in that system in here. And then we have the whole thing pressing against an elastic beam with strain gauges on both sides. So that's a fairly loose, fairly compliant system. All right, so this compares friction coefficient as a function of normal force for all three machines. At the top, we see the friction microprobe data, and here we're going from about 10 millinewtons to 100 millinewtons. There are 3 experiments per test condition there. And here we're traveling between about 0.25 and 0.3, and declining eventually to about 0.1, close to 0.1 in friction coefficient over the range of that machine. Below it then, going from 1 newton to 10 newtons, the laboratory pin-on-flat machine, same specimen materials now. This almost looks linear. I don't know whether I'm going to claim a three data per condition, whether that's linear or not. But we note that it goes from about 0.7 or 0.72, 0.73 on average down to about 0.5 here at the highest load condition. Now, that 10 Newton load happens to overlap with the low end, the 10 Newton load here on the Cameron Clint machine, a heavy duty machine. But we notice then at 10 newtons down here on the pin on flat, now we remember we have the same ball diameter, the same oscillating frequency, the same normal load, just two different machines. At 10 newtons here it's down to about 0.5, 10 newtons here it's up to about 0.78, close to 8. And then it declines again as we up the load. So if you wanted to plot all these 3 on the same plot, you have the friction probe data at the lower end, and then almost parallel curves higher for the mid-sized machine and the heavy-duty machine. But the nominal friction coefficient isn't the only thing we can look at in these experiments. Another attribute of the friction behavior is the range of friction coefficient. So at steady, we allow it to come to steady state, measure the maximum observed friction coefficient, the minimum observed friction coefficient. Just look at the range as a function of the applied normal force. For the friction microprobe, here we see again the range in friction, the variation in the friction coefficient is going down as you increase the normal force. So it's going from slightly above 0.1 down to very, very steady. Now on the other end of the scale, for the Cameron Clint machine, going from 10 that's rather sloppy and rather compliant. There doesn't seem to be much trend of the variation of friction coefficient with the change in the normal force. So that any trend which might have been indicated by the stiffer machines on either end of the load range spectrum are certainly disguised within this mess up here. But then we might say, well, let's think about what's going on now. If we have a very small contact area, perhaps a microstructural element such as a carbide or grain boundary or some defect in the material might have a greater effect because it's a larger proportion of the contact area if you have a very small contact area. If you have a larger contact area, then perhaps you might have, say, 3 to 10 disparities at any one time, and they may dance around as a function of time, and at any one time, their effects may more or less average out. So the same size microstructural feature would in proportion have less effect than we would expect the variation in the friction to be decreased as you increase the nominal contact area or the apparent contact area. So if we plot the data for the pin-on-flat tribometer and for the heavy load Cameron Flint machine as a function of friction coefficient variation as a function of the square of the track width, and then obviously it's proportional to the apparent contact area. Unfortunately, I couldn't measure any track widths on friction microprobe. There was barely any evidence that anything had happened to the specimen. You could look at the tip of the slider, see maybe a little darkening, no pronounced grooving. You could look at the surface of the flat specimen, and if you were lucky, you may see a very small thin scratch, but usually you couldn't find it. On the other higher load machines, you see what is typical of what they call severe metallic wear with a great deal of ductile tearing and significant plastic deformation. So here we're plotting for the pin-on-flat tribometer the square of the track width versus the variation in friction coefficient, and just about all you can do is draw an envelope around the data and say somewhere in the midst of this thing, our data lie. There isn't even a very good correlation with load. I threw in some extra data here with 15 newtons, but still very unsystematic or unclear variation. However, with the Cameron Flint machine, there seems to be a variation in the friction coefficient range decreases as the track width increases. And this is essentially a cross plot. You see the same thing with load. So we can talk about how to plot them. So let me talk about four findings here. Nominal friction coefficient decreased as the normal force increased on all three machines, but the measured values varied between machines. The variation in friction coefficient during sliding was machine dependent, and it also depended on the type of sensor system that we used. And maybe that's a subject of more workshop discussion next week, Dr. Rabinowicz's workshop next week. Practical models for friction submit in inadequately lubricated machines, that is to say machines in which there's some solid contact occurring, should focus on the degree to which the materials and the machine characteristics must be taken into account. There may be some systems in which it's sufficient to model the frictional behavior based on the interfacial mechanical properties and material properties on either side of the interface, and in other systems you need to take the role of the machine characteristics in closer account. And for practical models, should in general strive to predict the expected range and distribution of friction forces to be encountered during operation, rather than to assume that there is a single value of friction coefficient that describes a machine. If I went to a designer and said, well, if you use this material combination, you're likely to see a maximum friction coefficient of such and such, and you might even see a minimum friction coefficient of such and such. During normal operation, we would expect the friction to be so-and-so. And this would allow the designer to prepare for excursions, which are not uncommon in the operation of machines. So I would suggest that maybe modeling ought to look at distributions rather than individual values of friction. And to summarize, if I don't say a limerick, some people in the audience very disappointed. And usually in giving tribology talks at conferences, I throw in a limerick at one point. And so I'd like to finish up with this limerick I composed in honor of the workshop. And it goes, high up in the mountains of hearts, we broke friction into its parts. No model prevails, which handles all scales. The answer eludes current arts. So
well, I always introduce you Peter as a well-known poet. I could have taken that risk. The decision was taken at the beginning of this session that we wouldn't have questions in between the presentations, but you have in fact finished 5 minutes earlier than you might have done, so I think it would certainly be sensible to have some questions.
I'm getting asked, Tabor, the only question I'd like to ask is how the surfaces were cleaned. What did you know about the surface?
right, well,
What was that question?
how the surfaces were cleaned.
Thank you.
After polishing, they were degreased with first acetone and then ethanol. Now I know you're going to say there are all kinds of hydrocarbons all over the surface. However, I think the goal was that we should operate these machines in the normal mode as much as possible. Expose them to the ambient, be as dirty as the real world becomes within reason. We prepare them in the same way. We swab them with solvents.
Erwin?
Irwin Singer.
All right. Or do you want to shout?
I'll shout. I was unable to guess while you were showing your data at what contact stresses the experiments were run at. Could you say briefly what they were and to what extent might there be some correlation with friction and stress? I assume it was elastic range, except for perhaps the last one.
Well, do you mean the elastic contact stress, or do you mean the apparent stress?
The calculated mean Hertzian stress.
Well, I've only felt justified in doing that for the friction probe, where I didn't see any obvious plastic deformation. And in that case, I think at the 10-gram load with the 1 millimeter ball, it was something like 1 gigapascal.
So they were, all three were
That
very
overlapped.
high stresses.
But I didn't know whether you could really, well, that is an overlapping condition for the range of the second machine at the lowest load, it turns out. So we're looking at about the same contact stress. Because you make the ball bigger and increase the load, and sort of compensates. You get about the same contact stress.
Did I understand correctly that your second measurement you had more accurate time information?
Yes.
And if so, is part of the reason you see extra fluctuations in that experiment due to the fact that you can resolve things on a shorter time scale, or are you still averaging over some respective time scale?
No, we're looking not at the nature of individual fluctuations. I understand what you're saying. You perhaps could catch some higher and some lower under that condition.
Right.
However,
The range you quoted, is that instantaneous forces over the mean load, or is that averaged over some?
we essentially took several traces of reversal cycles after the system had reached steady state, and then sort of came in with a caliper and just what's the maximum, what's the minimum. I would say that if you look at the Cameron Flint, for example, which gives us RMS massaged or filtered value, if you look at the oscilloscope, which comes with the system, those variations that we saw in the strip chart weren't out of line with the instantaneous variations that we saw on the oscilloscope. But this is a subject that, each one of these issues, I think we could spend some time on discussing.
You've talked a great deal about Mr. Cameron, so I'll share a little story with you. Can I just show this? You used a Cameron Plinth machine, and many years ago, I think it was, some people remember this, maybe 20 years ago, he chose to do this classic rwin experiment. He took a piece of steel, and he submerged the contact in the mineral oil, and he put some stearic acid in it. And he varied the temperature to something that Tabor did in 1940, I think, or 45. He changed the temperature and measured the friction coefficient, and then he found scuffle. Sorry, you shouldn't see this bit here. And then, because the interest was, because he believed that bound lubricant was being absorbed. And he said at this point the lubricant desorbed. So this was the critical temperature for the desorption of the lubricant. So he then did a piece of thermodynamics, which anyone can do. He plotted the logarithm of the concentration of stearic acid in the solution against the reciprocal of the critical temperature. And if you fiddle the equations, you can show that that slope is the isosteric heat of absorption. It's a very plausible experiment to know. Then Wallace-Hurst came along, and he changed the spring stiffness of the machine, and he showed he could change the critical scuffing temperature from about 180, I think, even down to 20 by changing K. That's the Cameron-Plymouth machine.
There are a couple of things I didn't mention. One is I should mention non-intentionally lubricated.
But it would have contamination inside.
All right, so that's why I said it's not unlubricated, it's not intentionally lubricated. And in the other case, the humidity varied between about 50, maybe plus or minus 10%.
Well, I guess at this point the discussion is getting really interesting and more general and moving off into stick-slip motion, and perhaps we better stop.